Hi everyone, this is Prof. K speaking, and today we're going to talk about integrated rate laws. So the learning objectives of this video are to explain the form and function of an integrated rate law. And in this video, we're going to perform integrated rate law calculations for a zeroth order reaction. And then in part two, I'm also going to perform an integrated rate law calculation for a first and second order reaction. And then we will also talk a little bit about how we can identify the order of a reaction from concentrated time data using these integrated rate laws. So just to review and remind you about what we talked about in the last video. So for some reaction, you can have a rate which is zeroth order or doesn't depend on the concentration of A, for example. If something is first order with respect to the concentration of A, then its rate is equal to K times the concentration of A. And if something is second order, then rate is equal to K times the concentration of A squared. So the exponent of A tells us the order of A. And this rate is a reaction rate. So it's not necessarily the rate of decomposition of different components depending on the equation that you have, but it just represents how rate depends on concentration. And if we want to describe how the concentration of A changes with time for a zeroth order reaction, we will, we will have an instantaneous rate that looks like this. So if we have a zeroth order reaction, then the rate of decomposition of A with respect to time is going to just equal K. And so what this says is that A will be used up over time, depending on how the rate changes. And for this specific reaction, we're assuming that we're sort of using 1 mole of A in the particular system. It could be different in a different reaction set, but this is what's true in this particular problem. And so if we wanted to look at the instantaneous rate of a first order reaction that uses up 1 mole of A every time the reaction proceeds, then the change in concentration of A is going to equal K times the concentration of A for this first order reaction. You can write the same expression for the change of the concentration of A with respect to time as a function of K to the A squared for a second order reaction. And so this derivative is telling us how concentration is changing with time. So we have a ddt of concentration. And for a first order reaction, it is a function of A. And so that makes this relationship a little more complicated than if you just had dA dt of K, which means that the rate is constant. We don't have to worry about it. It will never change with time. And while this expression can show us how concentration changes with time at some point in time, it doesn't necessarily tell us what the concentration is at some specific time. So if I gave you an initial concentration in some system and I gave you a value for the rate constant, what if you wanted to be able to predict what the concentration would be after 30 seconds? This rate doesn't tell us that. It just tells us how A would be disappearing in our system. And so if we look at it on a plot, the actual concentration in this black line is what we're interested in. And the rate that we're currently talking about is this change in concentration versus time. So we can get data about how the concentration is changing, and we want to tell from that what the order is, or we want to tell if we can write an expression that would allow us to predict concentrations at times where we don't have rate data for. And so if you remember in math, if you want to move from a derivative to the actual function, you end up having to do an integral. So I'm going to do a sample integral with a simple function, and then we're going to do some integrals with the rates that we're interested in. And so as a math reminder, this plot here shows a function f of x, which is equal to x squared. And so currently the information that we have is the derivative of that function. And so if you take the derivative of f of x with respect to x, and we take the derivative of this whole equation, then you get that the derivative of f of x is equal to 2x. And this is what the current form of our decomposition looks like. And so this is how you would go from a real function to the change of rate. But the problem we're facing is, how do you go from something that looks like a derivative to something that is a function? And so we can rearrange this and separate the sort of changes of rates, and then do an integral of that whole expression to try to get back to f of x. And so this is how you sort of reverse the fact that a derivative has been done. And in this particular example, I'm using an indefinite integral, which means that I haven't put any limits on either side of my integral here. And so the limits here are missing. This is an indefinite integral. And I'll talk about why I care about that in a second. But if you integrate this, and you might remember this, or it might be something you haven't learned yet, or you shouldn't focus too much on being able to do this. But if you take the integral of this, then you get f of x on this side, and then you integrate 2x, and you end up getting x squared plus some constant c. And so this is a method where we can go from something that looks like a rate or a change in time or a change in x, and we move to what the actual function is. And if we have some data, we can use it to find our constant. So if we know something about our system, then we can find this constant. And so this is how you would solve a rate expression in order to get a function. And I mentioned using an indefinite integral. But what we can also do is we could use a definite integral where we move from 0 to x. And when you do this, you can recover a function that is the integral of these, but over some specific range. And when you do a definite integral, you still integrate whatever the component is, and then you plug in f of x and f of 0. And on the other side, you plug x and 0 into x squared. So f of x minus f of 0 is equal to x squared minus 0 squared. And so if I wanted to, I could rewrite this as f of x minus f of 0 is equal to x squared. So compared to the indefinite integral, we could see that our c here is going to equal this f of 0. And so this is a way to find our constant if we have it. So we can do the integral either way. And I just wanted to show you and remind you that this exists, because this is how we're going to be deriving the integrated rate laws. So I'm going to start with a 0th order reaction, which has an instantaneous rate of negative dA dt is equal to k. And so if we start with that as the beginning of our integral, and we integrate from 0 to some time. So we start a reaction, and then we want to know what concentration is at some time later in this system. Then we can rearrange what's inside these parentheses so that we separate the dA and the dt. We do this integral, and we get negative a is equal to kt, and then we have to evaluate it over the limits of our integral. And so that means we plug t into both sides, and we plug 0 into both sides. And so when we do this, we get negative a of t plus a naught of t, or the initial concentration, is going to equal kt. And so all I've done here is I've plugged in sort of how a depends on t, how a depends on is at the initial condition, and then I plugged in t and 0 over here, but the 0 term disappears because it's kt minus k times 0. And then we can rearrange this, because ultimately what we want to know is the concentration at some time given an initial concentration. So now, if I tell you the initial concentration of some system is 1 moles per liter, so 1 molarity. If I tell you that that concentration exists, and I tell you that K is 0.5 moles per second, then I can ask you, to find a new concentration at any time in seconds. So this allows us to start to calculate concentration using time. And so this expression is what we call the integrated rate law. So we integrated the instantaneous rate, and now we have an expression that tells us concentration given initial conditions and some rate of change. And so if you are looking at data for a zeroth order reaction, you see that the concentration steadily declines as a function of time. And so as time passes, you lose the same amount of molarity per second or per minute or whatever. And so what's nice about this is that if you know your integrated rate law, then you can take a plot like this and derive what your initial concentration is, or what your KT, or what your K is, or your rate constant reaction. So if we rearrange this integrated rate law slightly, we have the concentration at some time is equal to negative KT plus the initial concentration. And this is in the form of y equals mx plus b, where y is the concentration at some point in time, m is negative k, and b is the initial concentration. So from this rate data, you can predict k from the slope. And so this helps us better identify what a rate constant is using a slope or a line of best fit if maybe our data isn't as pretty as this data that I generated. And we can start to calculate concentrations at times that are between the collected data. And so the integrated rate law gives us a lot of opportunity to calculate sort of new features of this system. So as a sample, if you want to calculate what the rate is, or if you want to calculate the concentration at 45 seconds, you can just plug it into this expression. So this is a sample calculation that you can try by yourself and that we'll practice more in class. But based on the above data, what would A be in 45 seconds? And so what you would plug in here is that your concentration at 45 seconds is going to equal 3 molarity minus 0.02 moles per second times 45 seconds. And then you just plug that into your calculator and you get a concentration per time, which is really useful because then we can provide guesses, or we can see if our goal final concentration is 1 molar, then we can plug that in here and find out how much time it takes to solve this. And so it gives us another tool with which we can anticipate concentrations at different times using kinetics data. And so in the next video, I'm going to do a similar, I'm going to derive the integrated rate laws for the first and the second order reactions.